So here we are in the last tutorial looking at a multi-objective solver. Now the first thing we're going to do here is to add in our multiple objective solver. So if you double click in the canvas and type in Octopus, the multiple objective solver. This is one of many solvers that exist at the moment, but to demonstrate the principles for you, I've chosen Octopus. The next thing we're going to do is type in number. Let's get two number bins, or it would help if I could type. And two stream gates filters. Those are going to go into 0. And then we want to feed in null to our 0 gate. Actually, let's just delete that one, so we'll copy this logic. Add in another number bin, and let's put a panel so that we can interrogate what we're looking at. Factor of safety here. And our gate is going to be exactly the same as with our single objective solver. We want that same gate. Okay. Then we're going to divide. Whatever this number is. Sorry. We're going to place this number under 1, so 1 over the factor of safety. The reason for this is because this multi-objective solver is trying to reduce all of the 3 figures we're going to be feeding it, and so we want to increase the factor of safety. That's beneficial to us. We want the highest factor of safety, and in order to drive that up, we need to place it under 1. The smaller the fraction, the better. So that's going to be fed into our solver. Right, let's copy all of this, group it, copy it, and change the title here to number coats. Great. Yeah, the gate is exactly the same as before, but this time we want to take the source for the data right back to the number of coats. Number of hooks. And this one, what we're doing here, we are looking at the factor of safety, so let's just go and grab that factor of safety that we outputted earlier here, 3.33 at the moment. Brilliant. Let's group that one too. Right, so now we've got factor of safety, 1 over factor of safety and 1 over number of coats. And then we want the same volume of material as with our single objective solver. We want that to be added too. That's interesting to us. So let's create a panel. And this is going to be the names of our axes. It'll be 3 lines. First one, X, volume of timber. Second one, Y, 1 over factor of safety. And then Z will be 1 over the number of coats. There we are. Let's make this a different color so that it stands out. We need to right click and choose multi-line data for this. And feed that into a text bin. Right, so that will be one of the phenotypes for the solver. Let's give a bit of space. Same thing for the values of the current solution. So let's rename this. values of current solution, and that will be, again, let's hold down shift so we add another one in. That will be our second phenotype coming in. Right, but now we actually do want to feed in values here. We don't want to feed in just this text. So first one, volume of the timber, comes from up here. Second one, 1 over factor of safety, hold down shift. Third one, 1 over number of coats, hold down shift. There we go. Just going to hide those wires. That happened off screen, but I think you get the gist by now. Right, now we need to do the last thing, which is to select the genes, the genomes. I'm going to select 4 here. I'm going to add in the number of hooks. Otherwise, we'll do exactly the same as with the single objective optimizer. Let's add in the number of hooks. We don't need to hold down. We do need to hold down shift, which I forgot to do. Add in the diameter of the base. One more time, add in the depth of the base. No idea why they chose to feed the wires in different directions. I guess they think it looks cool. Maybe it does. I don't know. Whatever. Right, okay, so there we are. We've got all the information fed in. We know that we are trying to minimize the volume. We're trying to minimize 1 over factor of safety. We're trying to minimize 1 over the number of coats. So what this is going to do is we're going to get a solution space in 3 axes. We're going to have a graph plotted in 3 dimensions, and that will develop over time something called a Pareto front, which will demonstrate the minimum value of the combination of formulas, or a combination of each solution. That will make a lot more sense when you see the graph itself. I'll let it run for a little bit and then we can discuss the results. So what we have here is a 3-dimensional plot. I'll make it bigger so that we can see. We have a 3-dimensional plot. Each plot represents a single solution, a single combination of the width, the diameter of the base, the depth of the base, the diameter of the top ring, and the number of hooks. Each one of these represents a solution, and we can reinstate it if we like. You see that change? We can reinstate any of these solutions and see what it found. But you'll notice that there is a curve. Obviously, we can never achieve 0, 0, 0 for each of these attributes we want to minimize, but we have something called a Pareto front in 3 dimensions here, which is absolutely brilliant, I think. And it means that we are able to choose how much weighting we give to, say, the volume of timber. If it means that, for instance, the number of coats is maximized and it only takes a little bit more timber, then we might choose one of these. Although here we can see that it takes an enormous amount more timber to create pretty much the same number of coats. We can look at that for each axis. I'm going to reinstate one roughly about here to see what a approximately optimal solution is. So the maximum number of coats for the minimum weight, the minimum volume of timber, and the highest factor of safety. Do we see? Let's see. So the factor of safety of 2 is not bad, to be fair. That does look strange. Doesn't look like it. It doesn't look like it's quite a way off being unstable, but there we go. None of the coats are touching, and we can find any other solution we want to by just navigating around that again. So there we go. There is a multi-objective optimizer. Go and have some fun. See if you can come up with some more interesting designs for a stand. A lot of these functions you can reuse, and the logic will apply. So it's just a case of changing this geometry here, really, and making sure that if you're doing something that's non-symmetrical, or if it's asymmetrical, that you place the tipping point in the correct location, that you work out what the least balanced condition is for that particular design. Most of this, again, you will be able to keep and you won't need to remake. But it'd be really awesome if we could come up with some more interesting, creative stand designs. So there you go. There's the last video.